Good morning. Get this going. All right. So welcome to this webinar where we'll go over the results of a recent research study we did funded by NITC entitled Improving Walkability at Signalized Intersections with Control Strategies. The contributors on the title page here really were quite important to the research, including the City of Portland, City of Mesa, and City of Flagstaff. So there'll be a brief introduction, and then I'll talk a bit about the background and goals of this work. I'll talk about the different pedestrian control strategies that we investigated in this research. I'll talk about how we developed our pedestrian priority algorithm and the deployment of that. And we'll finish up with some conclusions from this work and a couple of recommendations. Why is this work important? This figure from 2014 shows that we're still at 83% of our trips by a car, truck, or van. It's important to get people out of their vehicles and then into alternate modes of transportation for a variety of reasons. One of which congestion, other reasons, such as just simply as public health. Another reason why this is important is that delays typically affect pedestrians disproportionately. In that most pedestrian trips are much shorter than vehicular trips. So if they catch a 30 or a 60 or 90-second delay, if the trip is only 5 minutes, it really is a big part of their trip. On the right side of the screen here, you see the City of Portland's priority triangle with pedestrians at the top. This is flipped from what we typically have seen implemented at a lot of locations historically in the United States, with private automobiles at the bottom and peds at the top. This is all well and good, but how do we translate this a policy for pedestrians first into specific operational strategies at our intersections? Looking at the background of this, there hasn't historically been a ton of research about signal control strategies focused on pedestrians. There has been some work looking at the leading pedestrian interval and the exclusive pedestrian phase known as the Barnes dance, but those are really focused on safety. There are other efficiency-focused options that we'll talk about today, including a shorter cycle length, actuated coordinated timing, and free operation, and while these have been looked at in other regards, they really haven't been looked at with a focus on pedestrian operations. So the goals of the research project one of the goals was to look at the efficiency impacts of these strategies on all users. Coordination, which was our kind of our baseline, since that's typically what we see deployed along arterials in the United States, the use of an LPI, the exclusive pedestrian phase, shorter cycle lengths, free operation, and actuated coordinated operation, as well as develop and implement a pedestrian priority algorithm. Key here is that we're looking at the impacts on all users, so not just pedestrians, but also motor vehicles. The first strategy with this figure from the signal timing manual is the leading pedestrian interval. All that happens in this is that at the start of phases 2 and 6 in this example with our LPI on the major street, we give a walk signal to the pedestrians a few seconds before green is given to the concurrent vehicular movements. This can be from 2 to 7 seconds. It's really up to the discretion of the practitioner that's operating this how long it would be. But that's typically how that is implemented. And on this figure here, you see this gentleman walking with this cup of coffee on the cold morning with the walk signal, and then the vehicles do not have the ability to turn across his path. From a safety standpoint, there's been documented reduction in PED vehicle crashes at intersections. This strategy can also provide a level of comfort to pedestrians, which is really a good and a bad thing. It's nice to feel good, but that level of comfort may not reflect the reality of the safety of the situation that the pedestrians are in. From an efficiency standpoint, this strategy will increase overall delays due to lost time. This can be somewhat mitigated with the use of a split LPI, where only the right-turning vehicles are held and not the concurrent through movement, but there still is an increase in delay. And that magnitude really depends on the length of the LPI, the cycle length, and where the LPI is implemented. If it's just on the major street, if it's just on the minor street, or if it's on both streets. Implementation, there's a variety of factors that go into whether or not you should implement an LPI. Items such as crash history, ped volume, schools, if you have older residents nearby, how much extra delay can you handle at the intersection, what's the visibility. There's not a real good hard and fast guideline for this. We've done some recent work that was published at the TRB conference earlier this month, looking at this, but we haven't found a real good hard and fast guideline for this. The City of Toronto does have some informal guidelines, but the next strategy is the exclusive pedestrian phase, or the Barnes dance. Here we see in this ring diagram, we have that noted as phase 12, where we simply give pedestrians, the ability to cross at any direction of the intersection. Here's a picture of a typical striping pattern for that, so they can cross on either leg or diagonally across the roadway. This also has a documented reduction in ped vehicle crashes at intersections. However, it can increase pedestrian signal non-compliance. This is due to the efficiency impact of this, and that the use of an exclusive pedestrian phase increases delay for all users, pedestrians included. We've added another phase to the ring, and that does increase delay. So after a certain duration of delay, pedestrians are less likely to wait for that phase, especially if it's a low-volume intersection. And of course, the actual magnitude of the increase depends on the length of the exclusive pedestrian phase, as well as the cycle length. An exclusive pedestrian phase is best suited for intersections that have a high volume of pedestrians, as well as turning vehicles. So where that operational paradigm of the vehicles and the pedestrians sharing that space simply breaks down. It must be very careful to weigh the cost of this, because there is a large increase in overall delays, and you may have that increase in pedestrian non-compliance. But this is a strategy that can work where traditional pedestrian accommodations do not work very well. Free operation, or just basic fully actuated control. In this operation, each intersection operates independently of adjacent intersections, so there are no artificial holds or a cycle length based upon a coordination. The intersection is then optimized without consideration of the other signals. This leads to greater flexibility and responsiveness. However, good detection is necessary on all approaches for high operational and safety performance. As far as safety impacts, none were quantified in the literature, and as I say that, I want to make sure that's understood that is regarding pedestrians. We didn't I don't have information as far as vehicle safety in relation to free operation, but that's in relation to pedestrians. On an efficiency standpoint, this can reduce overall delays when the view receive values are fairly low. This is really a trade-off between major and minor street user delays with higher volumes. Use of free operation will reduce minor street pedestrian delay as well as minor street vehicular movements, but it will increase major street vehicle delay. And of course, this is detrimental to coordination. Effectively, what you're doing here is you're allowing the intersection to operate based upon the demand that's present, as opposed to a coordinated operation where it's operating based on the demand that you expect to be there. So you provide a long artificial green on one arterial while the other direction must wait. It's common to see delay decrease overall user delay for all users when using free operation over coordination in most cases. Free operation is best suited, again, looking at from a pedestrian standpoint, where we have locations where there are long spaces between adjacent intersections, so effectively where coordination really would not work very well. Again, locations where coordination may not be a priority. This could also be implemented based upon a time of day operation to prioritize pedestrians. So if there are some times of the day when you'd like to use coordination to focus on the vehicles, but other where you'd rather focus on the pedestrians, free is one way to do that. Free operation also tends to work well when intersections have balanced volumes on the major and the minor streets. Another option from a pedestrian standpoint is to shorten the cycle length. We end up with cycle lengths of a certain duration, sometimes very long durations, because we're looking to meet coordination along an arterial. So whichever intersection has the longest cycle length or the longest natural cycle length on our arterial, we may end up with something like that, which could be much longer than necessary for adjacent intersections. So pedestrian delay, just like vehicular delay, is a function of the cycle length. So the idea here is to simply shorten the cycle length to reduce pedestrian delay. From a safety standpoint, with regard to pedestrians, there are no impacts that are quantified in the literature that we're aware of. From an efficiency standpoint, this does reduce pedestrian delay. They're waiting a little bit less between when they push the button or for the walk sign to come up if we're in pedestrian recall. It encourages signal compliance because the pedestrians can see those indications turning over quicker, so they know that they don't have a very long time to wait until it'll be their turn to cross. It typically will increase efficiency of all the users. Again, there are some cases where this would cause an increase in delay, but generally we see an increase in efficiency for everybody with a shorter cycle length. Okay. When to do this? This strategy is best suited for off-peak time periods, other low vehicular demand periods, when it's important for an agency to keep the signals coordinated. NACO's Urban Street Design Guide and PedSafe also recommend short cycle lengths to increase compliance and efficiency. Another strategy for reducing pedestrian delay is to use actuated coordination. So in this strategy, we stay in coordination, and in the figure you see right here, what we do is the last portion of the coordinated interval, 5 seconds, 10 seconds, 15 seconds, whatever that value is, the signal is allowed to gap out. So as opposed to placing a long hold on that phase, even if there are no vehicles there to utilize the green, the signal is allowed to operate actuated for that phase, and that can then move on to the successive phases in the ring structure. This allows the signal to be much more responsive to the actual field conditions while still holding a green for coordinated movement. From a pedestrian standpoint, there are no safety impacts that we're aware of that are quantified in the literature. There has been some work looking at this looking at the use of actuated coordination on vehicular delays by the folks at Purdue. This causes fewer split failures and a decrease in V over C ratios. Now, of course, this isn't the case that you have the ability to actually gap out early. If the vehicle volumes are so high, then you simply wouldn't see much of a change. Using fixed force-offs and fully actuated coordination can reduce the delays for the non-coordinated phases. You're simply allowing those phases that follow the coordinated phase 3, 7, 4, 8, and 1 and 5, you're allowing them to get their green a little bit earlier in the ring structure. Prior research has shown that this can cause a decrease in minor street pedestrian delay, and that last bullet point, we have some numbers on that later in the presentation here. As far as implementing actuated coordination, again, it's best suited for locations where, or during off-peak where there are lower vehicular demand periods, but there still is that desire by the agency to keep the signals coordinated. It can also help when you have a lower major street demand and a high minor street demand. So you could use this in the peak period at a location where you simply just don't have that many vehicles on the minor street, but still want, on the major street, but still want to provide coordination to whatever vehicles are there. This does require detection on the main line because you have to be able to know where vehicles are to be able to gap out. So this does incur additional detection, and maintenance costs. The next strategy deals with the permissive length. The permissive length is the period of time after the yield point, so that point in the cycle where you can call a non-coordinated phase. It's the window of time where non-coordinated phases are allowed to be called. Okay, so essentially, if you think about this in operation, it's a larger period of time in the window where if you were to, if you're simply dwelling on the coordinated phase because there's no activity, if you press the PED button on a minor phase or a vehicle pulls up on a minor phase, you're allowed to serve that phase right away or shortly thereafter, as opposed to waiting for another additional cycle to pass. Okay? So increasing the length of this window can allow the other movements to proceed a bit quicker without having to wait that long period of time. Again, from a pedestrian standpoint, safety impacts, we're not aware of any that are quantified in the literature. On an efficiency standpoint, Dr. Kothuri did work on this in her doctoral dissertation, and it was shown that this can decrease the minor street pedestrian delay and also reduces delay for non-coordinated phases, as was shown in some earlier work. Okay. Again, this is best suited for locations where, or for time periods that are off-peak with lower vehicular demands, again, when there is that desire to keep the signals coordinated. In this case, major street demand would be lower, and then the minor street demand is high. There's been kind of a recurring theme in the last 3 or 4 different strategies where we're looking at shortening the cycle length, increasing the permissive period, using actuated coordination at time periods when we may want to still be coordinated, but we want to try to improve the operation for pedestrians. And so we're effectively trying to kind of toe the line between vehicular and pedestrian objectives. So that led us to this pedestrian priority algorithm, which the goal of this is to simply change the operational pattern based on a volume input. It really is a very simple form of a traffic responsive pattern change. So when you have volumes that are above a certain threshold, the intersection operates in its normal operational plan. Say it operates coordinated above that threshold. But once the volume drops below a certain threshold, a pedestrian plan is chosen for operation. And this can be from any of the other, this could be any of the options that I've already spoken about before. Free operation, change the permissive length, and others that were discussed. So on the left side of the screen here, you see a simple flowchart that shows this operation, or the operation of this algorithm. We start up here. We have our normal operational plan online. We monitor the detector volumes for a certain amount of time, and after the end of that time period, let's say that's 15 minutes, if the volumes are above the threshold, then we go to our pedestrian priority operational plan, and again, this is chosen by the operator. We continue to monitor volumes for another, say, 15 minutes, and then we make that same decision point again, where if the volumes are still above the threshold, excuse me, if volumes are still below the threshold, then we'll continue with the pedestrian plan, but if they're now above it, we'll go back up to the top. On the right side of the screen, you see a screen grab from the ASC3 controller. We originally developed this within the ASC3 controller using their the onboard logic processor. This allowed us to do a hardware-in-the-loop simulation of the algorithm, as well as we deployed it in the field on the ASC3 controller at one of our locations. So what's this threshold? This figure was put together by Dr. Kothuri in some of her previous work. On the x-axis, we have the pedestrian actuation frequency. The y-axis, we have V over C on the major street. And if we look at the different, kind of regimes of operation, when we have V over C below about 0.5, regardless of how many pedestrians we have passing through the intersection, free operation really is our best bet for operations. When V over C values are above 0.8, we typically would look at some sort of coordinated operations. But there's that time period, or sort of that operational period where the V over C values are between 0.5 and 0.8, where we still would likely want to do coordination. But when pedestrian values are high, we do ped recall, but when they're a bit lower, we'd want to manage that pedestrian service. And this is where we feel that our algorithm really would really works well. As part of this work, we did a simulation of a couple of the different alternatives. Our network was on the east side of the Portland metro area. The corridor is Division Street with the three intersections of 119th, 122nd, and 130th. The middle intersection, 122nd, is the intersection where we change the operational strategies during the simulation. The results of the simulation. Get the next slide here. If we have four strategies that we investigated. We have our coordinated base case, actuated coordination, free with the algorithm, and the way this was done is that we had a 90-minute simulation period. The first 30 minutes were to populate the network. We had vehicular volumes at a high level for the first 15 minutes of the actual collected data period in the simulation. We then dropped the volume inputs to below the threshold for 30 minutes, and then went back up for 15 minutes. So you really will see the results of actuated, coordinated, and free about halfway between them for the free with the algorithm. I do want to call attention. So when we look at just average vehicular delay for our two coordinated cases, actuated and then the base case, we don't see much of a change, but we do see less vehicular delay for free with the algorithm, and then just general free operation. When we look at PED delay for 2 and 6, okay, we have 25 seconds for the base case, but then for actuated coordinated, we bump up to 36 seconds. The reason this was the case is that our coordinated base case was rest and walk, and then the actuated coordinated case required the pedestrian to push, or the simulated pedestrian to push the button. Okay, so that's why we see an increase in delay from the base case. We do see an increase in delay for free with algorithm and free from the base case as well. Again, this was our major street pedestrian movement. So we were dwelling on 2 and 6. We had rest and walk, so the PEDs there had lots of options and time to cross the street. we look at the PED delay on phases 4 and 8, we see that in our base case, we have about 45 seconds of delay. When we have actuated coordinated, free with the algorithm, and then free, we decrease somewhat and then significantly the pedestrian delay. Looking at travel times, we do see that travel times are impacted. So eastbound and westbound, that's our phases 2 and 6. So we do see that looking from the base case up to free, that there is an increase statistically significant in several of the cases. That's what the asterisk stands for. And then northbound and southbound, we see correspondingly a decrease in travel times when we go with the more aggressive pedestrian strategy. The next step of this work was to actually deploy this in the field. At the onset of this work, we had planned to deploy the algorithm on the ASC3 controller at 2 locations, and then using the 2070 controller running the Voyage platform at 1 location. During the course of the project, about a 22-month period, the support for Voyage software effectively went away. We had some implementation issues with the ASC3 controller at a location in Mesa, and the staff at Mesa, Arizona, took it upon themselves to develop this algorithm within a Raspberry Pi, which you see right here. The Raspberry Pi is just a simple computing device that you can use to do basic computer algorithms. Let's see. So, determination of that threshold, I'll revisit that for just a moment. If you recall, a few slides back, I had the photo or the picture of with V over C values on the y-axis and PED actuation on the x-axis, looking for that kind of sweet spot where we should operate this algorithm. What you see here is a data output plot of vehicle counts from the Raspberry Pi. This is just for 1 detector. That's why the counts are, I believe these were 5-minute bins, 5 or 15. That doesn't matter for the example here, but the x-axis is time of day and the y-axis is vehicles. So if you look from one peak to the next peak, that's about 24 hours. So when we sat down with each of the agencies to decide, at what level should we operate this algorithm, we pulled this plot out and just looked at where do we want to draw that line. So, I have this thick red line here. If I have the algorithm set for this threshold right here, when I have volumes that fall below that threshold, then I would operate the pedestrian priority plan. When volumes are above that threshold, I would operate the intersection in coordinated operation, so our baseline case. So this right here shows a situation where we're really fairly aggressive with operating the pedestrian priority plan. If I were to shift that bar to be a bit lower, now we're being much less aggressive for the pedestrians, but we're favoring coordination during more times of the day. So it really is up to the operator to choose at what level to operate, what level to place that threshold. Of our 3 sites, the first site is in Mesa, Arizona. This is on Brown Road, just north of downtown Mesa. It's an east-west arterial. Speed, I believe, is 40 miles an hour. On the left side, we have Center Street. The right side, we have Mesa Drive as the adjacent signalized intersections. This actually is a Hawk or a pedestrian hybrid beacon that is operated by an ASC3 controller. The blue dots in the photo indicate locations where we have Bluetooth data collection devices for travel time generation. The second site is in Flagstaff, Arizona. This is on the north side of Flagstaff. NAU campus is about a mile or so south of this location. Here is our intersection here. The major movement here is actually a westbound left turn to go southbound. This is the Flagstaff Medical Center, so there's a lot of vehicles going in there. We have adjacent intersections that are part of a coordinated arterial just east of our study location. We also have had Bluetooth data collection units out to collect travel time to see what that impact was, but unfortunately, somebody in Flagstaff decided to burn open one of the cases and steal the guts of one of them, so we did not get Bluetooth travel time information at this location. The third site is in Portland, Oregon, and this is that same arterial where we simulated the algorithm and all the other different cases. Right here, we also have Bluetooth travel time, but due to delays at this site with implementation, this is the location where we started off looking at doing this on a 2070 with Voyage, ended up doing it with an ASC3. During that time period, the city of Portland needed to move the Bluetooth devices to another location to collect travel time, so we did not get travel time location at this site either. So the outcomes of the deployment, what you see here on the results, we've got 2 weeks of weekdays before, so Monday through Friday times 2, so 10 days, and then two weeks of weekdays after. Here are the different time periods during the day with differing cycle lengths. Mesa actually operates a couple different coordination plans between 6:30 a.m. and 3 p.m., but the cycle length is the same at 100. And then we see the same thing for after. What we're really looking at here, the time period that we thought we could really impact operations, is during that off-peak time period. So if I look at that 6:30 a.m. to 3 p.m., which is our 100-second cycle length, I see that my average pedestrian delay goes from 49 seconds before to 22 seconds afterwards. At the Mesa location, actually at all the locations that we did the field deployment, the pedestrian operational plan was that of free operation. So we see a drastic reduction in travel time here, or excuse me, a drastic reduction in pedestrian delay here. And if we look at the travel time during those periods, we actually see that westbound travel time went down 5 seconds and eastbound travel time went down 2 seconds. Now, we don't have, we didn't collect data at the adjacent intersection, so it's hard to really infer very much from these data points, except that it was heartening to see that we didn't really cause a negative impact on the vehicular operations during that time period. We also do see a decrease in pedestrian delay during the overnight time period, but during the PM peak period, we see actually a slight increase in pedestrian delay. In Flagstaff, we had 1 week of data before and 1 week after. Again, there's no travel time information here. So we're looking at that midday time period in Flagstaff. That's from 8:15 a.m. to 4:30 p.m. We do see a slight, we see a 7-second decrease in pedestrian delay, which was good to see. We had a few more ped calls on the after than the before data. We do see that during the PM plan, though, that pedestrian delay went up significantly. We at both Flagstaff and Mesa, we used a video detection unit to drive this algorithm, and in our experiences just being at the Flagstaff site, we saw a number of operational issues with that video detection unit. So we've got a feeling that we had an issue with detection during that time period. At the Portland site, we had minor reductions in pedestrian delay. This was a location where the vehicle volumes on phases 2 and 6 versus 4 and 8 were really fairly balanced, so it wouldn't ideally be a location we'd pick to try this out, just because we wouldn't expect to see a lot of additional chances for pedestrians to cross because of the balanced volumes. But looking at the all-day time period from without the algorithm to with the algorithm, we did see a slight decrease in pedestrian delay. And then looking at just that 10 a.m. to 1 p.m. time period, we saw a slight decrease in pedestrian delay as well. If we look at all the different strategies that we've talked about here, on the left side of the screen we've got pedestrian delay, the right side of the screen we have vehicular delay, and they're organized where to points where we, or in a manner such that at the top of the screen here we have generally more delay for a strategy, and at the bottom of the screen we generally have less delay for a strategy. So with pedestrian delay as well as vehicular delay, we see the most delay if we use a barn stance or that exclusive pedestrian phase, and then at the bottom of each list of strategies we see free for the least amount of delay. Again, this is generally changing of specific parameters at any given location may cause or may show a different ranking of these strategies. But these were our findings generally from the research, from our simulations for this work. Looking at our conclusions, the LPI and the barn stance may improve safety, but they typically decrease delay overall. For free operation and shorter cycle lengths, we do typically see reduction in pedestrian delays, but the impacts on safety are not known. Our field deployments corroborated our simulation results, which is heartening to see. It does feel good to see it actually work in the real world. The city of Mesa was a very strong partner in this work. They developed using their own personnel and time the strategy or that algorithm on the Raspberry Pi device, and they had already at the conclusion of this project 6 months ago, they had already deployed this algorithm at several other trail crossings within the city that weren't part of this work. Generally, like anything else in traffic engineering, there is no right solution. Whichever strategy you choose to implement is based upon your operational objectives for a specific location and those characteristics of a specific intersection. So, looking at recommending any of these different strategies, if we look at a barn stance, typically this would be a good strategy to use if we have very high pedestrian or right turning volumes that create that need to completely separate the modes. So either our pedestrians are choking the right turns, or the right turns are choking the pedestrians. That didn't sound right, but anyway. The LPI, split LPI, we want to use this when either the vehicle volumes or the geometry of the intersection cause a challenge for the pedestrians to get into the crosswalk, to allow them to establish themselves out there for the crossing. Shorter cycle lengths, this satisfies our need to operate in coordination while we trade green bandwidth for reducing delays for the other users. Free operation is our most aggressive strategy, resulting in lower delays for most users, but that does come at the expense of Main Street users. So you typically would see an increase in delay for the Main Street traffic. Actuated-Coordinated, this can provide an earlier minor street walk if the possibility of Main Street vehicle gap out is there. This is useful for low to moderate pedestrian volumes. If you have pedestrians that come every cycle, just by the nature of this operation, this wouldn't provide much assistance. But if you did have a pedestrian every 3, 4, or 5 cycles, then you would see a bit more of a benefit, because just simply keep in mind that the cycle will have to catch back up with itself. So if we end the coordinated green earlier in one cycle, we're going to have to have a longer green the next time through. We do have a few publications on this work. Our project that was funded by NITC, the final report has been published. We had a paper in Transportation Research Record that I don't have the exact numbers on it yet, but the conference paper link, the conference paper is linked here, which is sizably the same paper that was published. We did put together an application guidebook as part of this work, but that is still in publication, so we do not have a link for that quite yet. Just again, want to acknowledge NITC and TREC for providing the funding for this work. Colleagues at Portland State University, as well as the graduate student and undergrads that worked for me at NAU during this work, and really most importantly, the 3 cities, Portland, Flagstaff, and Mesa, who without their willing to try this out in the street and willingness to sacrifice some of their time to help us with this, would not have made it possible to see the real-world results of this research. Our contact information is listed here. And that's the end of my slideshow.
Great. Thank you, Ed. For those viewing the webinar, please feel free to continue to submit your questions if you have them, but we do have a few questions already, so we'll go ahead and go through a few of those. All right. So let me start off here. For the shorter cycle lengths, did you notice, did those help slow traffic speeds?
So the shorter cycle lengths, our analysis of that was in simulation, and Sirisha, you can correct me if I'm wrong on this, but we did not directly look at travel speeds of the vehicles as we were analyzing the results for that, so I really can't comment on that.
Yeah, that is correct. We just looked at delays across the different user types, but we did not look specifically at traffic speeds.
Okay. And what do you consider short when considering shorter cycle lengths? And at what level does delay start to increase? Is it related to the number of lanes at the intersection or other variables?
So at our intersection, again, this was, let me scroll down to this slide here that shows the one we used, the best one I have here. This was the intersection that we adjusted the cycle lengths at. The natural cycle length was 110 seconds, and in this work we dropped it down to 70 seconds and raised it up to 130. Again, this is all in the simulation, and we didn't see delays start to creep up as we dropped it lower and lower and lower. We did see a few anomalies in the simulation when we had only a couple of users. We might have seen delay go up for a couple of users as we got to really short cycle lengths, just based on when they arrived. But the results we saw in this work were really as you would expect. As we decreased the cycle length, delays generally went down for users, and as the cycle length increased, delays generally went up. We did not do any kind of geometric changes to our network, so we really can't comment on what it would do with different configurations.
Okay, great. At what level of pedestrian volume does an LPI be warranted and justified, and can you point to any literature on this?
Sirisha, you want to handle this one?
Yeah, sure. I think there is still a lot of need for research on that particular question. As Ed said earlier, there is not enough guidance out there on what exactly the condition should be. But LPI is mainly a safety strategy, so more than volumes, we definitely want to look at the crash history at the intersection and see if there are conflicts and what kind of conflicts between pedestrians and those turning vehicles. But I do not have a good answer for you in terms of the exact number of volumes.
Typically what you see is a lot of different rules of thumb being used by different agencies. And that's, they've used what works for them in their situation. So unfortunately, there isn't really hard guidance on when to use this. We just did a paper on this for TRB, and I think we're still waiting to see if it'll be published or not, but it is in the conference proceedings about looking at an LPI as a cost-benefit comparison. So looking at the delay that's incurred to the vehicles, and comparing that with the reduction in conflicts or crashes for the pedestrians. So that is out there, and there is some work in that area, but we're not to the point yet where we have any firm guidelines that I'm aware of.
All right. And do you have any data to see the vehicle delay impact on the test sites with regards to the PED priority?
Can you say that again?
Do you have any data to see the vehicle delay impact on the test sites with the PED priority?
No, we didn't. On our real-world implementations, we didn't collect vehicular delay. We were limited to collecting information that we could get out of the traffic controllers. At the site with the ASC, actually all three sites had ASC3 controllers operating, so we used the event-based data logger on board to look at the time between when the push button was depressed to when the walk indication came up. We didn't collect video and record anything else like that. We just simply didn't have the budget or the manpower to do that.
Okay. And then you referred to something called PedSafe. Can you explain what that is?
Sirisha?
Yeah, that's just a document that's put together by the Federal Highway Administration, and it looks at, I believe, different strategies for improving pedestrian safety.
Okay, great. Did you see any research related to pedestrian delay and signal crossing compliance? And the question recipient said, and I would also imagine signal crossing compliance would be related to volume.
Yeah, Sirisha, go ahead. I think you're more qualified on this than I am.
Yeah, so there is no definitive research on this, but I have seen some papers which state that as the delay increases, pedestrians definitely start taking more risks, and so one paper, I believe it was the German Highway Capacity Manual, I think, or something like that, but said anything above 30 seconds is where the pedestrians might engage in more risky behaviors. And so, again, 30 seconds might be too optimistic for a lot of locations. So, and as we said, it totally depends on each individual location, but one outcome of this work that we'd like to see is to use your existing controller, like as Ed mentioned, the ASC3 controller has an inbuilt data logger. You can use that and start recording and tracking your pedestrian delays at different intersections and locations, and then mining that data, you could easily come up with a threshold that would be acceptable. And this threshold, again, could also change by time of day.
Okay, great. All right, and what is your opinion on recalling all PED phases?
Personally, I think it works in certain areas of town and works if the volumes warrant it, either the pedestrian volumes or the vehicle volumes. But again, that's one of those strategies that really I think is location dependent. I think it works real well in downtown areas or locations where you expect to have a lot of pedestrians crossing really all the time. Otherwise, it certainly does increase delay or can increase delay for the vehicular users.
All right, and did you do any research or find any studies about delays for pedestrians and motor vehicles and flashing yellow arrow emit phases?
No, we did not.
Okay. All right, here's a quick one. Can you explain what a fixed force off is?
So a fixed force off means that, let me go back to a ring diagram here. Here's the next one. So the fixed force off, if I look at each of the different phase durations on this ring diagram, and I presume that the size of it or the width of this is the duration of the split. A fixed force off means that the force off stays at the same point in the cycle regardless of the duration of the phase. So operationally, what this means is that if phases 2 and 6 in this example go all the way to the barrier, phase 3, if there's a lot of volume on phase 3 and it maxes out, it will max out at this location right here. Let's say that's 15 seconds. We have a 15 seconds, I'm sorry, it will force off after 15 seconds. That's the duration of the split for phase 3. In the event that, let's say we terminate phases 2 and 6 10 seconds earlier, since that force-off for phase 3 is fixed at this location, it can then time its original 15 seconds plus the 10 seconds from the early termination of phases 2 and 6, so it can go up to 25 seconds. The converse of that is a floating force-off, where the force-off moves with relation to the start of the phase within the cycle. So in that case, if we had floating force-offs in that same example where 2 and 6 terminated 10 seconds early, phase 3 would only time for 15 seconds because that force-off would move with the start of the phase.
Okay, great. Thanks, Ed. All right. Is there evidence that reduced pedestrian delay increases the number of people who choose to walk? If so, what's the relationship between reduced delay and pedestrian activity? This information seems essential if we want to establish a target for reducing pedestrian delay.
I'm not aware of anything. Sirisha? I'm not aware of anything either.
Okay. All right. Has anyone ever experimented with double exclusive pedestrian phases, where you would let cars move one way, then pedestrian move always, then cars move the other way, then pedestrian move always? Presumably, this would increase pedestrian compliance.
So there's an intersection in DC that's right by the red line. I think it's the whatever line that gets out by the Verizon Center, where they actually run the barns dance in between. So we run north and south green, have north and south pedestrians, then we run a barns dance, and then we run east and west. That's the only thing I've seen that's been different as far as a different take on the barns dance. So they're actually, and in DC you can actually see it, right, because they have the countdown timers for every single walk duration. So I haven't seen a location where it's kind of hopped back and forth between the two. Have you seen something like that, Sirisha?
No.
Now that's a good idea, but of course, then you're adding 2 phases to the ring, so you're going to increase delay even more. Which, depending on where you want to do this, it might work out well, or it might cause some issues. So.
Yeah. All right. One of the tools we use in Toronto is half cycle at mid-block signals. This may be equivalent to a short cycle length included in this presentation. Do you have any thoughts on that, or how the half cycle could be implemented?
I think it's a good idea, personally. We didn't directly look at that in this research, but it certainly accomplishes what we're trying to do by looking at by reducing that cycle length at locations where you want to provide more or earlier crossing opportunities for pedestrians.
Okay. All right. So the exclusive pedestrian phase with diagonal crossings may have safety implication on visually impaired or blind pedestrians. Any suggestions what to use in terms of audible signal or messages to help them cross diagonally?
I am not an expert in that area, so I will defer comment on that.
Yeah, I have to concur with Ed. I'm not an expert either, but I think the cities that are actually implementing it would probably be able to will have more information.
Okay. Did your study look at the number of vehicle stops or the impact on fuel consumption and air quality?
I think we have that information in the simulation results, but we didn't focus on it for reporting results of it. So you won't see that in any of the funded work of the reports.
Okay. And we have a comment also from a listener. So they introduced the Barnes Dance in Northwest Portland on Cooch Street. As a pedestrian, I find the wait times much less preferable than the four-way stop. Why not just stick with the four-way stop if it seems more responsive to need than a signal?
That certainly is a possibility, and I'll let Peter Kuntz know the next time I talk to him. But in all seriousness, it really depends on the vehicular volumes out there. After you get over a certain number of vehicles, a four-way stop will cease to function properly, and you have to go to a signalized intersection. So I'm not intimately familiar with the details of that intersection operation, but I would presume if they went from a four-way stop to a signal, that there was a volume reason behind that. Sirisha may know more about that because that's the area where she lives.
No, I was going to say the same thing, that it was probably related to the vehicular warrants as well. But we can definitely check with Peter and get back to you with more information.
Okay, great. And well, I guess we have time for one more question. It's a little bit longer question, so I will try to read through it here quickly. It's from a citizen. She writes, I'm a citizen without a good grasp of terminology. Apologies. We have a system being implemented in my city, in Halifax, where the vehicle signals are controlled by sensors. So once the fixed length pedestrian countdown runs out, the vehicle signal may remain green for a variable length of time based on how many cars still need to move through the intersection. The system is being implemented in places with and without push buttons. I've noticed that this creates a significant amount of pedestrian non-compliance if pedestrians see the vehicles moving in the direction have a green light they want to cross to, and of course it also increases delays for pedestrians. Therefore, I'm very frustrated that it is being implemented in this day and age in a dense urban areas, a supposedly more progressive system. So her question is this what would be called actuated-coordinated, and if not, what is the correct term? And could you comment on this approach and whether you think it is a good approach and why?
It sounds like it's actuated-coordinated. Typically, you would not, so an actuated-coordinated, you're relying on the pedestrians to push the button to call the phase. So you're actuating that pedestrian phase of the pedestrian movement. If you're not going to have push buttons, the signal should be operating in what we'd call pedestrian recall, where that pedestrian phase comes up every single time. So if that's the case, if the pedestrian phase or the walk is not coming up every single time the concurrent green comes up and there is no push button, I would call the city and ask them about that, because that does not seem proper to me. But the operation you're talking about does sound like actuated, the typical actuated coordinated operation.
I'd just like to add on and say, so in the city of Portland, they also use this strategy, which is resting and walk. So, so the situation that you described, where the pedestrian phase ends before the vehicular phase, does not happen for the main street phases. So the pedestrians would see as much green or walk time as the vehicular street phases. So that could be one strategy to pursue. But the flip side to that is if there is demand on the minor street, then you have to go through the pedestrian clearance time, which would again lead to excess delay on the minor street. So there is a bit of trade-off here, but the city of Portland has in their policy that they will rest and walk for the major street phases.
Okay, great. All right, well, thank you everyone for joining us today. I think this concludes our webinar time. Thanks again to Ed and Sirisha for sharing their work. You can view other professional development offerings on our website at nitc-utc.net. This concludes our webinar, and enjoy the rest of your day.